It's time for another amazing chemistry video with Mr. Stapleton. Proudly sponsored by Farming Doing Nice Coffee.
Okay, welcome to this follow-on video from the KC equations or KC expression video. You really need to make sure you watch that first before you jump into KC calculations. In that one, I'll go through that equilibrium constant is our concentration of products over concentration of our reactants, and I go through what the KC value tells us. So if you get a KC value equal to 1, that means it's complete. If it's a KC of 1, it means it's even, and if you get a KC value less than 1, it means the reaction is incomplete. So you need to keep that in your head when you're going through and doing these calculations. So there's a couple of steps when you're going through and doing these, okay? And what you need to be able to do is make sure you follow out and use this table that I'm about to show you every time you're doing these calculations, okay? So what you're going to see is you're going to see the question just flash up here in a second, basically where it's talking about the reaction in the Haber process, which is the first one I went through before. And we've got some starting concentrations of nitrogen and hydrogen, and then we've got an equilibrium concentration of ammonia. Okay, so you might want to write that down, okay, so that you can see what I'm going through a second for this question. All right, so the Haber process is this one. Okay, we have some nitrogen gas, and that's in equilibrium with, that reacts with some hydrogen gas, and is in equilibrium with 2 moles of ammonia gas. Okay, so when we're going through and you've got your equilibrium equation like this and you're trying to work out your Kc value from your actual concentrations in the question, okay, you need to draw up a table, and your table looks like this, okay. So what you've got, firstly, all right, is I always find it good to actually put your species across the top here, N2. I bring the mole number down, all right, the stoichiometry value number down, and you'll see why in a minute. So 3H2 and 2NH3 here. And then you've got 3 rows across your table, okay? So the first one you want to have is your initial concentration. You want to have your go-to, is what we call it, all right? And you want to have your equilibrium value. All right, so this is your table that you'll set up anytime you're doing one of these calculations, all right? Okay. So when you're going through and you're using this, it's important to put in the values and read the question carefully before you start doing that. So your question will either have 2 things in there. It'll either tell you the number of moles in a certain size container, or it will tell you the concentration, okay? So for this first question, what it's telling us is it's just telling us the concentration. It says that initially we had 6 moles of nitrogen gas. We reacted that with 10 moles of hydrogen gas. Okay, so 6 moles of nitrogen, 10 moles of hydrogen were allowed to react and come to equilibrium. At equilibrium, okay, we had 2 moles of ammonia. All right, 2 moles per litre, that's the concentration. So because the actual question says the concentration in moles per litre, all right, we can put that straight into our table. Okay. Now what we're going to do is we're going to start going through and filling out the rest of our table. So it says initially we had 6 moles per litre of nitrogen and 10 moles per litre of hydrogen, and they were allowed to reach equilibrium. So that means the initial initial concentration of our ammonia was 0. So we know that our ammonia has gone from 0 up to 2. So that's increased by 2 moles per litre. This is where it's really important that you've actually put your mole ratios up the top here, because the changing of concentrations will occur in the same line as our stoichiometry values. So if this goes up by 2, this will go down by 3, this will go down by 1. Okay, so I've tried to do a very simple one to begin with because that's a 1:3:2 ratio. So this one went up by 2, okay, this one's going to go down by 3. Now if you're ever unsure of what values to use in here, the one that you've got the value for, like this one, going up by 2, 2 divided by 2 gives us a value of 1. So then you multiply. 3 by 1 is 3, 1 by 1 is 1, so that's how much it goes down by. All right. If your products are going up, your reactants must go down. So now we can work out our equilibrium concentrations of nitrogen and hydrogen. 6 minus 1 gives us 5 moles per litre of nitrogen. 10 minus 3 gives us 7 moles per litre of hydrogen gas. So now what we've got is our equilibrium concentrations, okay? We can put that into our Kc expression, Okay, Kc expression, if you remember, okay, for this one from the previous one, is going to be, and I'll put it down here, Kc equals concentration of ammonia squared, because there's a 2 there, over the concentration of nitrogen times by the concentration of hydrogen cubed. Okay, so what we can do is put these values in. All right, so I'll just show you here. So Kc equals 2 squared, because that's our concentration of ammonia, all right, over 5 times 7 cubed. Okay, so you can put that in, and I'll just quickly work that out for you. Okay, so what we've got is 4 divided by 5 times. So you're going to get a Kc value here of 0.002. Okay. Now, hopefully you can tell, all right, from relating that back to down here, that that's a value that is much less than 1. So that tells us that this reaction is incomplete. It very, very heavily favours the reactants. Okay. So I'm going to show you another one. Okay, and I want you to keep in mind this table, okay, because that's really, really useful. Okay, so you've just seen the second question flash up on the board, so up on the screen, I should say. So hopefully you've written that down, and it involves this reaction, or this equilibrium. Carbon monoxide with oxygen with carbon dioxide here. So hopefully you noticed a couple of different things about the question from the previous one. First one is that you would have noticed at this time it talked about how many moles we have and then a certain size container. Okay, so you'll notice with the carbon monoxide it talked about the fact that we had 8 moles of carbon monoxide. However, what it said is that that was in a 2 litre container. Okay, so 8 moles of carbon dioxide in a 2 litre container is going to give us 4 moles per litre of carbon monoxide. So it's really important you read the question and work out, okay, if they're telling you the concentration like it did in the first one, or if in this one where it's telling you how many moles you've got in a certain size container. So 8 moles of carbon monoxide in a 2 litre container gives us 4 moles of carbon monoxide in total. Okay, it also told us that we had 12 moles of oxygen, okay, 12 moles of oxygen in a 2 litre container gives us 6 moles per litre as well. Okay, we didn't have any carbon dioxide to begin with, so our initial concentration there is 0. All right. Now, the second thing about this, okay, is it told us the equilibrium concentration of one of the reactants. So it told us at equilibrium we have 6 moles of carbon monoxide. It's still in a 2 litre container, which means that at equilibrium we've got 3 moles per litre of carbon monoxide. So again, this is a little bit different from last time, and we don't have the product over here, we've got one of the reactants, but we then follow it through exactly the same way. So to go from 4 to 3, we know we go down by 1 mole per litre, okay? So keeping in mind the mole ratios here, this is 2, 1, 2, okay? So if this goes down by 1, see if you can work out what value we're going to be putting in here for our oxygen, how much it's going to go down by. All right. Hopefully you've done what I did in the last one and you've gone 1 divided by 2 is a half, and then that's a 1 up there, so 1 times a half, it's going to go down by 0.5. So this is going to be 5.5 moles per litre of oxygen. Okay. Carbon dioxide here is going to go up by 1. So 2 lots of a half is 1, so that's going to have a concentration of 1 mole per litre. Okay. What you can do is you can put this into a Kc expression. Okay, the equilibrium expression is this: concentration of carbon dioxide squared over concentration of the carbon monoxide squared times by the concentration of oxygen. Okay, so these are our equilibrium concentrations that we're putting in. If you do that, you're going to get a Kc value equal to 0.02. Okay, check you can do that calculation, check you get the same value. What that tells us is that that is a reaction that is incomplete, and again, it favours the reactants. Okay, so there's two ways that they'll ask you this question. First one was like in the first example, where they give you the actual concentration of the species and you just put them into your table. Second one is where they'll give you the number of moles and they will give you the size of the container, and all you've got to do is convert that into a concentration. You can do it both ways really easily. What you've got to do is just practice, okay? Use your table. Don't try and do it without your table. Initial going to equilibrium. If you try and do it without your table, you're probably going to run into trouble, okay? So I would always suggest using this. As always, if you've got any questions, just ask. Hopefully it's been helpful again. Good luck, guys.